Welcome to this webinar about lasers for Raman spectroscopy. We're going to talk about what are the most important performance parameters of a laser source when you're choosing a laser for a Raman spectroscopy experiment. We're going to talk about why they are important for different types of Raman applications, how you achieve these laser performance parameters from different types of lasers, and finally we're going to talk about how we here at Uniphotonics are characterizing our lasers on these parameters. We're going to limit the scope of this webinar to be about spontaneous Raman spectroscopy, so we're mainly going to talk about CW narrow line width laser sources. Okay, to start with, a little bit of background information. So, Raman spectroscopy is a powerful technique for material analysis, mainly because it offers fast, sensitive, and label-free chemical analysis. It's also pretty much completely non-invasive and mostly needs no sample preparation. The principle is based on inelastic scattering of photons from a sample under investigation. And in order to detect the frequency shift in this scattered light, it's necessary to illuminate with a narrow line with light source with very high level of spectral purity. The capabilities of Raman spectroscopy has made it a very popular analytical tool that is used across a wide range of application fields. Thanks to a lot of development of new laser technology, filters and detectors, Raman instrumentation has really been able to move out of the scientific laboratories and is not only used for material research, but also as a routine tool for inline process and quality control in several industries. For instance, for controlling the raw material and compound distribution in pharmaceuticals, for process control in petrochemical industries, in food and beverage production, and for forensic and fraud protection. It's also becoming more and more commonly used in biomedical research, and is also paving its way into clinical diagnosis with capabilities for cancer tumor detection and classification. So what are the basic laser requirements for a spontaneous Raman spectroscopy experiment? Here is a schematic picture of a simple Raman spectroscopy setup. A narrow line width laser source is illuminating a sample. Most of the light is Rayleigh scattered, but a small fraction of the light will interact with phonons in the sample material, lose some energy and get frequency shifted. And by blocking the Rayleigh scattered light with a filter and studying the frequency shifted light in the spectrometer, it is possible to determine the chemical composition of the sample. And here are the spectral properties of the laser that impact very much the performance of such a Raman spectrometer. First is there is the line width. The line width of the laser must be narrow enough so that all the neighboring Raman-shifted peaks can get resolved. But the spectral resolution of the measurement is also often limited by the spectral resolution of the spectrometer itself, which for a fixed grating configuration is set by the groove density of the grating and the focal length to the array detector. Many advanced Raman spectrometers have a spectral resolution of 1 inverse centimeters or even less, which means that in order for the laser source not to be the limiting factor for spectral resolution, it should typically be less than a few tenths of picometers. Then there is the spectral purity, which means how deep down from the laser peak you have to go to find any side mode emission, and how close it is to the main peak. The Raman scattering efficiency is very weak, so in order to detect the Raman shifted peaks, there must be no emission from the laser source at a level of at least 60 dB down from the laser peak in the region where the Raman signals are to be detected. Most of the material characteristic Raman shifts are found in the so-called fingerprint region, around 200 to 4,000 inverse centimeters from the illumination wavelength. Those shifts can rather easily be detected by blocking the laser light with the dichroic notch filter. However, there are in some cases of great interest to study much smaller Raman shifts, to look at peaks in the so-called low frequency region of less than 200 inverse centimeters. Recording Raman signals in the low frequency region is possible by using a VBG-based notch filter, which is much more narrow and can provide blocking of the laser light of more than 60 dB at as close as 5 inverse centimeters. This means also that the laser source must have more than 60 dB spectral purity at less than 5 inverse centimeters from the main peak, which at 785 nanometers corresponds to about 300 picometers. But it doesn't help to have a good spectral line width of the source if the wavelength drifts around during the data acquisition. So in order not to contribute to a decrease in spectral resolution, the wavelength drift of the laser should preferably be less than 10 picometers during the acquisition time, which could be on the order of minutes. And then finally there is a wavelength. And what is the best wavelength for a Raman experiment really depends on several parameters. So what is the best wavelength choice depends mostly on what material is being studied. But there are several other aspects that need to be considered. First, there is the Raman scattering efficiency versus autofluorescence. The Raman scattering efficiency scales with the wavelength with a factor of -4. So the Raman signal is much stronger at shorter wavelengths. However, there's usually much more autofluorescence from the sample at short wavelengths that can easily drain the Raman signals. Then there is the detector sensitivity. The sensitivity of commonly used silicon-based CCDs roll off quite rapidly after 800 nanometers. At longer wavelengths it's possible to use InGas or germanium-based detectors, but those are typically having a bit higher noise, which reduces the signal-to-noise ratio. An example how the selection of the wavelength can impact the sensitivity is shown here, which shows spectra of polyimide taken by a Jasco Corporation Raman instrument. One can see that the Raman signal is drained by fluorescence at 532 and 785, but can clearly be resolved when illuminating with a 4 or 5 nanometer laser. Considering those two aspects, it turns out that for many materials an illumination wavelength around 750 to 800 nanometers is the best choice. Wavelengths in the visible around green are often used with inorganic materials and for resonance experiments like SIRS and TERS. Violet to UV sources are often suitable for biomolecules. And for highly fluorescent materials, it's often useful to go further out in the near infrared at around 1 micrometer, even if the Raman signal is much weaker there. An alternative to avoid the impact of autofluorescence is to both illuminate and detect the Raman shifted light below 300 nanometers, as this is often below the spectral region of emitted autofluorescence, which is shown here. But the problem here is the availability of suitable laser sources in the UV and challenges involved with handling and detecting UV light. It should also be noted that the wavelength of the laser also has an impact on the spatial resolution of the system, as the smallest achievable spot diameter is proportional to the wavelength according to Abbe's law. We start with taking a closer look at the specular purity laser. We'll see here that this is a performance parameter which is of particular importance in low-frequency Raman experiments. Being able to measure low-frequency Raman shifts is interesting because it provides access to analyzing the lattice vibrations of molecular crystals. And this is of particular interest in pharmaceutical applications because it enables probing of the crystalline structure of the active pharmaceutical ingredient of a medical drug. Many such APIs are polymorph, which means that the same chemical compound can have different crystalline structures, and the crystallinity of the API can affect the efficiency of the drug for medical treatment. So this is an important factor to monitor, both in the development and in the production of a drug. One example is shown here, where the Raman spectra of griseofulvin, which is a medical fungal infection treatment in amorphous and crystalline forms, are compared. And it's clear that the crystalline state can most easily be determined in the low-frequency region. Another example is from a study over here, is from a study performed by a team at FDA in the US in collaboration with BW Tech, where they demonstrated fast mapping of the API distribution and crystallinity in several common off-the-shelf drugs by performing confocal Raman microscopy in the low-frequency region. This example shows mapping of an Excedrin pill, which is a medicine for headache and migraine. And it was pointed out in the study that as the low-frequency Raman peaks are typically much stronger than those in the fingerprint region, it enables faster mapping to work in this region. They also noted that thanks to advancements in narrow linewidth laser sources and notch filters, they are seeing that low-frequency Raman investigations of pharmaceuticals are starting to transition from the academic laboratories and into pharmaceutical labs and production lines. And next we will look at an example of the importance of the wavelength stability of the laser. The wavelength stability laser is not only important to enable resolving closely separated Raman peaks in the spectrum, but also to be able to measure shifts in the Raman peaks with high sensitivity. The exact spectral position of the Raman peaks from a material is dependent on many non-chemical factors that could be of interest to measure. One example is shown here, provided by Vitec in Germany, showing the capability to measure internal stress in silicon wafers to identify discontinuities by mapping the spectral shifts in Raman peaks with the remarkable sensitivity of just 0.02 inverse centimeters. And here's another example that shows the importance of the line width and the beam quality of the laser. In the Nobel Prize-winning work of Ben Feringa and his group at the University of Groningen in the Netherlands on molecular machines, they used Raman spectroscopy to study the rotary behavior and structural changes of the molecular motors in metallic organic frameworks, MOFs. This work was done in collaboration with Wesley Brown, also at the University of Groningen, and was published in Nature Nanotechnology. As they were looking at thermally sensitive and photochemically active compounds, it was found that it was essential to work with a narrow line width laser source with very little stray light and also with very high level of polarization extinction ratio. And finally, we have here an example showing the importance of the reliability and stability of the properties of the laser source in general. This is results from a study made by James Livermore at the Department of Clinical Neuroscience at Oxford University. He was using Renishaw RA816 Raman system to distinguish normal tissue from cancerous tissue in brain biopsies with very high accuracy by measuring the small spectral variations from these different tissues. And he showed that it's possible to do this in clinical settings in short time, it's less than 15 minutes, and with minimal sample preparation. His study shows that the potential of using Raman spectroscopy to guide surgeons in real time during operations to remove tumors effectively while leaving non-cancerous tissue intact, something that can have a drastic impact on the patient's health. He even managed to classify tumor tissue into specific genetic subtypes. And this is something that can provide very valuable information for surgeons when deciding on tumor resection strategies, as the health benefits of tumor removal are influenced very much by the underlying genetics of the tumor. Another aspect that impacts the requirements on the laser source is what type of Raman instrument it is used in. There is a wide range of different Raman spectroscopy instrumentation technologies and techniques that are addressing different types of applications. We can sort them into three different main groups. There is probe-based Raman instruments that are providing quantitative data used mainly for inline process control and quality control. These systems usually benefit from high laser power, but they usually use multimode fibers and therefore do not require TM00 beams. Then there are very compact handheld instruments used for in-field detection and identification, for instance for homeland security and fraud protection applications. And here the laser should be small, energy efficient, to be able to be battery powered. And here eye safety need to be taken into account as well. And finally, there are various types of Raman microscopes that provide high spatial resolution chemical imaging. And here the single transversal mode diffraction limited beam is very important to achieve high spatial resolution in confocal imaging. And it's also usually important here with the capability to eliminate at different wavelengths. So which lasers are suitable for use in spontaneous Raman spectroscopy? There are several types of laser technologies that can provide suitable performance here. One is diode pumped single frequency lasers. These lasers usually provide way less than a megahertz line width emission in perfect Gaussian beams and with a spectral purity well over 60 dB, extremely close to the laser peak. They're available at many wavelengths in the visible, in the UV and in the near infrared, but are less available in the 700 to 900 nanometer region. Most of the lasers in the corporate product lines are of this kind, and they're really perfect for low frequency and high resolution Raman spectroscopy. For wavelengths less or not easily accessed by diode pumped lasers, it's common to use various types of wavelength or frequency locked semiconductor lasers. These all have in common that the relatively broad emission from a semiconductor chip is turned into narrow line width or single frequency emission by locking the output to a narrow line width feedback from a grating structure. You get something like this. If the grating structure is integrated on the chip itself, we're talking about DBR or DFB lasers. Alternatively, the feedback is coming from an external grating element. The DBR-DFB lasers can be made very compact and cost efficient, but they are a little bit limited in power. The locking with external elements is a little bit more complex, but enables scaling to higher power levels. These lasers can be single or multi-transversal mode beams, depending on the output power. And in order to achieve sufficient spectral purity for Raman spectroscopy, it's typically necessary to use some kind of external cleanup filter so that you get a spectral shape, something like this. So these lasers are suitable for spontaneous Raman spectroscopy with a cleanup filter, but they are a little bit more challenging to be used in low-frequency Raman applications. The semiconductor-based lasers are often more sensitive to optical feedback than the diode pump lasers.
So several laser techniques can be used to design lasers suitable for Raman spectroscopy. However, the manufacturing of such lasers, delivering repeatedly the right spectral and beam performance over long time periods and at different temperature conditions, is associated with another set of challenges. To achieve stable frequency locking and single mode performance over a large range of operational temperatures, it is required to have a very thermomechanically stable construction for the laser.
For this reason, we are using HTQO technology for the manufacturing of all cobalt lasers. This is a manufacturing method that relies on high temperature curing of miniaturized high precision optics. All optical elements in the lasers are mounted onto a single temperature stabilized platform into hermetically sealed packages and fixed with a high temperature baking process. In this way, we can achieve very robust performance over varying ambient conditions, also from very sophisticated laser designs. Okay, by combining several of the laser technologies that we talked about earlier into our product platforms, the cobalt products in the 08, 04 and 05 series can offer lasers suitable for high performance Raman spectroscopy over a very large range of wavelengths and over many power levels. The 0801 series is particularly attractive as it offers a large range of wavelengths in the same compact package and with fully integrated electronics, and with beams that are coming out free space or fiber coupled into single mode fibers. Thanks to this development, we are now able to offer solid state based alternatives to essentially all laser lines that are traditionally achieved through gas lasers, such as the argon ion laser. And this is interesting because there are still a lot of Raman systems in the field that are equipped with gas lasers. And there's a general interest to replace gas lasers in Raman spectroscopy setups, as they take a lot of space and have more limited operational lifetimes. An example of this trend is shown here from the Raman facility at the University of Rochester in New York, where as many as 8 small solid-state lasers are used in their multi-wavelength Raman setup. And in many cases, when Raman spectroscopy is used for material research, it is valuable to use many wavelengths in the experiments to gain a deeper understanding of the material under investigation. And replacing gas lasers with solid-state laser alternatives saves space and lowers maintenance costs. And in this particular experiments, they were studying low-frequency Raman shifts, so they really needed excellent spectral purity of the lasers. When multi-wavelength solid-state lasers are being used, it simplifies the setup enormously to have them pre-mounted and their beams pre-aligned into a compact laser combiner solution. So for this reason, Hybrid Photonics offer a family of laser combiner solutions called the C-Flex. This C-Flex family of laser combiner solutions offers platforms for up to 4, 6 or 8 lasers. And it can integrate an almost unrestricted mix of the cobalt lasers suitable for Raman spectroscopy. So it's very flexible. And the C-Flex laser combiners provide a very precise and stable beam overlap. And all individual lasers are easily accessed via a back panel electrical interface. And the beam output can be free space or coupled into single mode and polarization maintaining fibers. And as an alternative to multiple laser lines and laser combiner solutions, Hybrid Photonics can also offer a very unique, broadly tunable single frequency laser source. It's called the C-Wave and is based on CW or continuous wave OPO technology with frequency conversion. It is available in 2 models that together cover the full spectral region from 450 nanometers in the visible up to 1.5 micrometer in the near infrared. It is broadly tunable, has a line width of less than a megahertz, and very good spectral purity at all colors. So it's really an excellent source for advanced Raman spectroscopy, especially for resonant Raman spectroscopy, where the illumination has to be carefully tuned in to trigger resonance effects in the material. So with this, I will hand over to my colleague Teresa, who's in the lab and who will show you a little bit of how we characterize the performance of the cobalt lasers, and especially in terms of these performance parameters that are important for Raman spectroscopy. So the line width, the spectral purity, and the wavelength stability.
I'm Teresa, coming to you live from Cobalt. I'm the technical quality manager here, and we're going to be looking around our manufacturing and test facility to see how we verify some of our key performance parameters. I'll be showing you the tests that we do on our lasers for Raman for bandwidth, spectral purity, and wavelength stability. All of these parameters are tested at different ambient conditions to ensure that there will be no performance degradation from lab to lab. Here we have one of our 08 lasers. You can see that it's very small and handheld. Here we have the port for the power supply, the key control box, and the communication cable. So everything is contained right here in this small laser head, the laser, the optical isolator, and the control electronics. So once you plug it in, turn the key, you're ready to go. No adjustments required. Here we have a Cobalt 08 NLD at 405 nanometers. It's mounted on a temperature-controlled base plate and shining into a Faber Pro. We have on the oscilloscope the single longitudinal mode performance as well as the spectral bandwidth. We can measure all of these performance parameters continuously with our acquisition software so that we can show the SLM performance, spectral bandwidth, and wavelength drift at different ambient conditions. In this measurement setup, we have an 08 DPL laser at 532 nanometers. The 08 DPL lasers are diode pump solid-state lasers, whereas the 08 NLD lasers are frequency-stabilized diodes. Here we have the laser mounted on a temperature-controlled base plate, coupled into a fiber, which is then used with the optical spectrum analyzer. The entire 0801 series is specified to have a spectral purity of better than 80 dB, which you can see being measured live right here. The temperature-controlled base plate also allows us to characterize that spectral purity over the entire specified ambient temperature range. At this test station, we have another Cobalt 08 NLD, but this one is 785 nanometers. Here we have the light coupled into a fiber, which is coupled into a wavelength meter, and we can monitor the wavelength stability over long periods of time. Here you see a span of an entire day, where we demonstrate the wavelength stability of less than 1 picometer at constant baseplate temperatures. We also have this laser mounted on a temperature-controlled baseplate so that we can cycle the ambient temperature from 20 to 50 degrees Celsius. Here you can see the wavelength stability performance in temperature cycling. So this 4 picometer range is the entire span over 20 to 50 degrees on the baseplate. Here you see the temperature cycle as monitored by the control software. Thanks for joining us here in our manufacturing and testing facility. I hope you gained some insight into how we characterize the spectral performance of our 0801 series lasers for Raman spectroscopy, and we'll turn it back over to Håkan.
So, to summarize, we can conclude that Raman spectroscopy is a very powerful technique for chemical analysis that can be used in many different applications and in many different industries. We have concluded that the most important performance parameters for the laser used in Raman setup is the narrow line width, the spectral purity, the wavelength stability, having the right wavelength for the application, and also very good beam quality, at least if it's for high resolution Raman imaging. We have also seen that there is now a very large range of solid-state based laser alternatives available for Raman spectroscopy, which makes it more and more attractive to start to combine those lasers into pre-aligned laser combiner platforms. And if that is not enough, we have also seen that there is now a possibility to use widely tunable single frequency laser sources perfectly suitable for Raman spectroscopy. Thank you very much for joining this webinar and listening today. I'd be very happy to try to answer any questions that you might have.
So thank you, Håkan, for a very informative webinar, and thank you, Teresa, too. So let's start with some questions. Is it important to know the underlying laser technology, or are they similar to operate from a user perspective?
In principle, as a user, it shouldn't be important to understand very much of the underlying laser technology, as long as the specification of the laser is suitable for that particular Raman experiment. And especially as laser suppliers like us, where we're trying to make it very convenient for the user to use lasers built using different laser technologies by packaging them in the same footprint with the same controller interface and so forth. But it could be important to understand that there are different laser technologies that are building up those lasers that are promoted as useful for Raman spectroscopy, because there are some performance differences between them. So it's important to keep that in mind when studying data sheets, basically, to understand that there are maybe some points in sometimes these data sheets can be quite dense. So it's important to look for differences between different wavelengths, essentially. And the main difference is that the diode-based lasers, they have a little bit lower spectral purity, so they need to have some kind of cleanup filter. And if you want to do low frequency Raman spectroscopy with the diode-based laser, you have to think about having a very narrow line with a cleanup filter, like a VBG-based one. And also the actual beam characteristics is a little bit different from the diode-based lasers relative to the diode pump ones. It's also something to take into account. But other than that, they are mostly operating in a very similar way if they're built in the right way. But it's important to take care when studying the data sheet, basically.
So this is a related question to do with data sheets. Which of the main laser requirements are most challenging to achieve, and what specifications are critical when comparing data sheets from different laser manufacturers?
Well, I can start backwards. I think the most important thing is to take exactly what I just said about keeping in mind that there might be the underlying differences in the laser technology, is to make sure that the important parameters for the Raman experiment are actually properly specified. So if the data sheet is missing strong indication or clear indication on what is specified from this laser, that should be a little bit of, then one should get skeptic. I think it's also important to be able to see performance data because even within the same kind of specification regime, there are differences in how the lasers perform from different manufacturers. But generally, I think that the most challenging laser requirement or performance parameter to achieve is to make sure that these lasers are locked to either single longitudinal mode or locked to the wavelength in a stable way. That is that the locking of the laser or the operation of the laser in a single longitudinal mode is done is intact also over long time frames and in varying temperature conditions. That I think is the biggest challenge in making those lasers. If you actually manage to stably lock them or stably run them at single mode, most of the other performance parameters they fall into place by themselves.
Next question: do the lasers need isolators?
Then I guess that we're talking about optical isolators here. Yes, I briefly mentioned that on the slide about the different laser technologies. I mentioned that the diode-based lasers, the frequency locked diode lasers,
they might be more sensitive to optical feedback than the dye pump ones, which is at least partially true. There is the topic of optical feedback is difficult because it's not just the level of feedback that is important, it's also to what extent it is very well aligned towards the laser cavity. So it really only has a chance to get back into the laser cavity if the laser is operating in some kind of confocal configuration against the sample. But in that case, the optical feedback, if it's into a diode laser-based laser, can impact the stability of the laser, or in the worst case also damage the diode. The diode pump lasers are less sensitive to this. For this reason, we often recommend that the diode-based lasers are used together with an optical isolator, which can be integrated in the package of the lasers, usually from our platforms. And these isolators that we offer, they provide a dampening of the feedback of about 20 dB.
In one of your slides, you mentioned the importance of the polarization extinction ratio. Why is the polarization important?
Yes, that's true. Normally, I would say that the information on the chemical composition of the material that is studied with Raman spectroscopy is not requiring polarized light. You can get the information about the chemical composition with any kind of polarized light. But if the illumination laser is highly polarized, it can give additional information about the material, especially for materials that are anisotropic in a way. For instance, like if there are crystals or polymers or even certain biomolecules can have an anisotropic response in the vibrational mode. So if the laser light is highly polarized, you can get some information about the orientation of the crystal structures or the molecules, which I guess was important in this study of the molecular machines, where they were studying the rotation of those molecules.
Another question. Are all your lasers single longitudinal mode?
The diode pump lasers that we are talking about here, they are all single longitudinal mode, yes, which means that they have very narrow line width, much more narrow line width than actually needed in Raman spectroscopy. The frequency locked diode lasers that we also provide for Raman spectroscopy are not specified to be single longitudinal mode. They still operate in narrow line width condition, and that comes from the fact that the longitudinal modes in a diode laser they are very dense, which means that even if it's not locked on one longitudinal mode, it would still be narrow line width, and it would still operate in a stable way. For the diode pump lasers, the separation between the longitudinal modes are much larger, which means that if you don't lock it onto one longitudinal mode, then the line width will be broader, and there will also be mode competition, which induces intensity noise in the output. So the short answer is all the diode pump solid state lasers that we provide are single longitudinal mode.
Another question. What is the warm-up time of the 08 series for the specifications to be fully met?
There is so the warm-up from cold start. If you provide power to the laser for the first time, there's first a time that it takes for the internal temperature controller to stabilize, which depends a little bit on the ambient temperature and the heat sink, but it's normally 0.2 seconds. After that, there will be a phase of running the laser in constant current mode, which means that the output power is not automatically or internally regulated. That phase is preset normally to 60 seconds, but it can be shorter if needed. So in total, from cold start to operation in active power control and according to all specifications would be something like 1.5 minutes. But again, if the laser has been powered up since before and you just turn on the laser emission, it is 60 seconds, but it can also be shorter, 2 seconds even.
Another question. Beam collimation is rather critical. Is the laser beam cross-section maintained over a long distance, say 2 meters?
Yes, collimation is important to avoid stray light and to have a well-controlled illumination area. All the lasers in our platforms, they come with a collimated output beam unless they are fiber coupled with specified divergence. So usually they come out with beam diameter about 0.7 millimeters and with a divergence of something like less than a milliradian, I believe it is. So the beam properties are maintained over a long distance, but the beam will be slightly divergent, although it is collimated there. But it's divergent. It's diffraction limited divergent, you could say. But we also have possibilities to customize the beam characteristics. If someone wants to have a more divergent beam, to have a larger beam diameter before focusing the beam onto the sample, that's something we can customize.
Right, the next question has 2 parts. So what considerations go into choosing the right operating laser wavelength? And what are the newer wavelengths being used in newer applications?
Can I ask you to repeat the first one?
What considerations go into choosing the right operating laser wavelength?
Yeah, that's a tough question. There is, as I explained in the beginning of the presentation, there are many considerations to take into account when choosing the right laser. I think one has to. It's difficult to generalize. Actually, it depends on the material that is to be studied. It depends on if it's in microscopy or if it's for quantitative analysis. It depends on if it's for research or if it's for industrial inline process control. It is very difficult to provide a specific answer to that.
Yeah, so I guess the questioner should go back and look at your first few slides again, where you address that.
Yeah, but we would definitely be happy to provide advice for those who are wondering what is the best laser. We'd be happy to hear what the application, the experimental setup looks like, and what is the target application, and then we can definitely provide advice on what we think is the best type of laser.
So the second part of the question was more specific. What are the newer wavelengths being used in the new application?
Well, we see, traditionally the wavelength around 785 nanometer has been very common for many applications. As the number of available wavelengths, especially from solid-state laser alternatives, are expanding, we see a lot of development towards using other wavelengths more adapted to the specific material that is being under study. So we see a lot of more increased use of visible lasers for different types of enhanced Raman spectroscopy techniques like SIRS and TERS on carbon materials. We see an increasing trend to use shorter wavelength lasers in the UV to avoid the autofluorescence. There is also to some extent an increased use of 1 micron laser with newer types of the InGaAs detectors, which have become better. So there are trends towards in all directions, I would say.
So this question touches on something that I think Teresa mentioned briefly. Are your lasers semiconductor laser diodes?
Yes. In a way, yes, and that's it. But more complicated, we can say yes. There is a diode laser in all our lasers. In some cases, the diode lasers is the source itself, and we use external grating elements to lock the emission of that diode laser to a specific wavelength. Otherwise, we use a diode, a multimode diode, as a pump source that is pumping a solid-state laser, which we build a cavity around to make a so-called diode pump laser. So all our lasers include a diode, but it's not in all cases that the emission is coming from the diode itself.
So, thank you, Håkan. That was our last question.
All right, thank you.
And thanks everyone for listening and for your question. And if your question wasn't answered, then you'll probably get it answered in an email. So bye, and thanks for listening and watching.
Thank you very much.